Okay, the last of our simple gas laws that we're going to cover is Avogadro's law. We have heard Avogadro before when we talked about Avogadro's number, 6.022 times 10 to the 23rd, when we defined moles. So it's the same guy that dealt with that value. Now what's happening in this one? Volume and the amount are what we're examining. The amount is going to be in moles. It could be in dozens, it could have been in grosses, but we deal with moles when we're dealing with molecules. So it's how many you have versus the volume. So when I say amount, it is a number amount, and moles is the handy one for that. Okay, so we're going to hold temperature and we're going to hold pressure constant. So I'm going to demonstrate this one for you right here in front of you with a handy balloon. Every one of you could do this demonstration. Ready? Okay, so we're going to imagine I'm not full of hot air and that I'm not getting hot air into here. We're going to imagine that the temperature is being held constant, okay? Whenever you use a balloon and you are working with a balloon, the pressure inside is working to match the external pressure, so we're holding pressure constant. And right now, this balloon has got a few molecules of air inside of it. But I am going to start blowing. Okay, so what happened to N as I put more air in there? The number of moles of gas went up. What happened to a volume? Well, you figure that one out. Okay, so as the number of moles went up, the volume went up, right? And what do we call that? Is that a direct proportion or is that an inverse proportion? Okay, so you don't have to just think about blowing up a balloon, you can actually blow up a balloon. Now we have to do the opposite. We'll let the moles out and watch the volume go down, although I doubt it'll stay handy for you to see. I don't want it to squeak, I want it to have fun. All right, so there it goes. There. So we've got our number of moles went down. I promise the volume went down as well. All right, so this is again a direct proportion. We've seen an inverse proportion with Boyle's law. We've seen a direct proportion with Charles's law. This one is a direct proportion. As a direct proportion, we can see all the same things that we've seen before. Oh, wait a minute, start it over. What are we doing here? Oh, there we go. Volume is proportional to the number of moles. That would be a direct proportion. Put a constant in it, get rid of the equal sign. Volume is equal to K times the number of moles. Here would be a more common way to see that written. V1 over N1 equals V2 over N2, as long as temperature and pressure are held constant. Now, application of this law. Usually, we aren't dealing with taking a gas and adding more gas and seeing how the volume changes. It is more common for us to use this concept that the moles and the volume are proportional when we're dealing with stoichiometry, okay? When we have a reaction taking place. We can think of the coefficients in a balanced equation in terms of moles, and we talked about that before. So we can say so many moles of this reactant plus so many moles of this reactant form so many moles of this product, and we thought about those balanced equations that way. If, and this is only if there are gases involved, and if we're holding the temperature and the pressure constant during the course of this reaction, then what we can do is we can think about those coefficients in terms of volume units. Pick one, liter, okay? We can think of them in terms of liters. We could think of them in terms of quarts, but we never do in chemistry, okay? And don't have to always think of them in terms of moles. Okay, so here's an equation. So we could say with this equation that 3 moles of hydrogen react with 1 mole of nitrogen to produce 2 moles of ammonia. That's NH3. We're used to doing that. Or we can think of it in terms of a volume unit, and this is only because they're gases. 3 liters of that hydrogen reacts with 1 liter, and when it's all said and done, we're only going to have 2 liters of gas, and there will be 2 liters of ammonia. So here it is in picture form, okay? We have the volume of 3 liters, whatever that volume is, 1 liter of the nitrogen, 2 liters of the ammonia being produced. And so this will be a handy conversion that we can do when we're doing stoichiometry if gases are taking place and if temperature and pressure are being held constant. Now, if a reaction gets really hot, you have to wait till it gets back to room temperature before you make measurements so that your final measurements are the same temperature as your initial measurements. So that's when we say held constant, that means between the beginning and the end of the experiment. So we're not going to do a calculation with this at this moment. We will eventually. We'll revisit stoichiometry here in a little while. But let's look at this here. What this gives us is a new road that we haven't seen before, which is up here at the top. Okay? Before, when we did stoichiometry in our previous chapter, we could only go from known country to unknown country, from moles to moles. But if we know the volume of one gas, let's say it's liters, we could get the liters of the other gas. Again, it's still coefficient bridge. We're still using the coefficients to get ourselves over from the known country to the unknown country. All right, so that's Avogadro's law. We've seen it defined. We've seen all, at this point, the simple gas laws, and this completes this lesson.